Chapter 3, Section 4 talks about perpendicular lines. We've already talked a lot about parallel ones, so we have to explain this relationship as well. So by the end of this lesson, you should be able to prove and apply theorems about perpendicular lines. So there's going to be a couple proving problems in this section. The shortest distance from a point to a line is perpendicular to that line. And this fact is used to define the distance from a point to a line as a length of the perpendicular segment from the point to a line. So that basically means that if we have a point out in space and a line out in space, and I want to know how far away that point is from that line, the shortest distance is not any of these crooked ones. It is the one that is exactly perpendicular to the line. So that means that this is the shortest. And that works every single time for absolutely any point. Even if we drew a point way over here, any other line that I draw isn't going to be as short as if I find one that is exactly perpendicular. So name the shortest segment from point A to line BC. So we have this line here, BC, and we have a couple segments from A to C, from A to P, and from A to B. So the shortest one, by that definition, has to be the one that's perpendicular. So the shortest segment is PA. And then it says to write and solve an inequality for x. Remember, inequalities mean not equal to, but still have a relationship. So if we look at the two values that we have, it's this line over here, I know the value, it's x minus 8, and this line right here, I know it's 12. So because we know they're not equal, because they're both not perpendicular, which one has to be bigger? Well, this guy has to be bigger because we know the shortest is from P to A. So I know that x minus 8, whatever that is, has to be greater than 12. And then just solve for x. So add 8 to both sides. So this value of x has to be greater than 20. And that's all they wanted us to find. So here's a couple theorems, and then we're going to prove a few of them. If two intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. So stop and think about what that means. Two lines form a linear pair. Remember, a linear pair means that they add to 180. And then it's a linear pair of congruent angles. So if they have to be the same and they add to 180, that means that they're both 90 degrees. And then the conclusion we can draw is that the lines are perpendicular because those two intersecting lines made two 90-degree angles. And then the perpendicular transversal theorem says in a plane, if a transversal is perpendicular to one of the two parallel lines, then it has to be perpendicular to the other. So we have these two parallel lines here. And the only information I give you is that it's perpendicular to one of the lines. Because these are parallel, that means it also has to be perpendicular to the other one. One more. If two coplanar lines are perpendicular to the same line, then the two lines have to be parallel. So this is kind of this last theorem, but backwards. I'm giving you that these two are parallel. And if they're both parallel to the same line, that means that these two have to be, or sorry, I'm giving you that both of these are perpendicular to this transversal T. So that means that we can conclude R and S have to be parallel. All right, so let's prove one. We're actually going to prove the perpendicular transversal theorem, which is this guy right here, that says in a plane, if a transversal is perpendicular to one of two lines, then it has to be perpendicular to the other line. So our goal is to prove that if one line is perpendicular to it, that we have two parallel lines so that we can say the other one is perpendicular as well. So let's take a look at what they give us. They give us that BC and DE are parallel, and they give us that this is perpendicular to one of the lines, that from A to D. So we need to somehow prove that that means that this is also a 90-degree angle. So let's think about what we know. So let's write down what they give us. We have the BC parallel to DE. So that was given. And then we know that AB is perpendicular to BC. So that was given. So because these two lines are parallel, think back to what we know about parallel lines. If they're cut by a transversal, and that's all AD is a transversal, we have corresponding angles. So remember, our goal is to prove that this one down here is 90 degrees. So this angle up here corresponds to that one. So based on that theorem, we know that angle ABC has to be congruent to angle BDE. And this is based on the corresponding angle postulate. And then think about what congruent means. It means that the measure of angle ABC is equal to the measure of angle BDE. Def of course, or congruence. And the only reason we bring up the measure is because I know what the measure of this one is. I know it has to be 90 degrees. So let's use that. I know the measure of angle ABC has to equal 90 degrees. And this is the definition of perpendicular lines. I know it makes a 90-degree angle. So then we can use the transitive property. If I know the measure of ABC equals the measure of BDE, and I know the measure of ABC is 90, that means that the measure of BDE has to also be 90 degrees. And this is the transitive property. And then finally, if I know that this is 90 degrees, that by definition means that these two lines are perpendicular. So we know that AD is perpendicular to DE, and that's based on the definition of perpendicular lines. And that's it. So now here's one that we kind of did for you. Remember that the perpendicular transversal theorem says that if one line is perpendicular and the other line is parallel to that first line, we can say that the next one is perpendicular. So that's what we're going to do for this one here. We are given that EHF is congruent to angle HFG. And then we're also given that FG is perpendicular to GH. Our job is to prove that EH is also perpendicular to GH. So this is what we want to prove. So think about where we're going with this. The only way we can prove that two lines are perpendicular are using either of these two theorems. If two intersecting lines form a linear pair, or if a plane has a transversal and one line is perpendicular to two parallel lines. So think back to what they gave us. They didn't tell us anything about angle measures, so we don't know if anything's a linear pair. The only other one we can use is this, the perpendicular transversal theorem. So our job means that we need to prove that these two lines are parallel so that we can prove the other one has to be perpendicular to it. So keep that in mind as we're doing this. Write out our statements and our reasons, and write down what they gave us. We know that EHF has to be congruent to HFG. And then think about what that means. What does that tell us, that these two are congruent. Well, if you think about these lines here, this line EH and this line FG, this right here is acting as a transversal. And if I know that these two are congruent, I can go backwards with the converse of alternate interior angles and say that that means that line EH has to be parallel to line FG. So now once we know that those two lines are parallel to each other, then we get to use what we just talked about. The other piece of information that they gave us was that FG is perpendicular to GH. So they told us this part right here. And remember, that new theorem that we learned says that if one of them is perpendicular to parallel lines, the other one has to be perpendicular as well. So that's it, we're done. We know from this that EH has to be perpendicular to GH based on the perpendicular transversal theorem. That if these two lines are parallel and this one is perpendicular down here, then that means that this one is also perpendicular over here. So that's it. You should be able to prove and apply theorems about perpendicular lines, and we'll do some more practice with this on Monday. Have a good weekend.